All right, today we're going to talk a little bit about what are called isotopes. So we've talked about the parts of the atom. We've talked about protons, neutrons, and electrons. We've said that the protons can't ever change. That if you change the protons, you change the element. Okay? Today we're going to talk about, well, you're right, the protons can't change, but one of the things that can change in the atom is the number of neutrons. Okay? So the number of neutrons and the number of electrons can change, and it can still remain the same element. Okay? Again, as long as the protons don't change. So when the neutrons change, so remember the neutrons are in the nucleus, and the nucleus is pretty sensitive. So when you change that nucleus around a little bit, it changes the atom. It's still the same element though, but a lot of times it's not as stable as another atom. But when you change the neutrons in an atom, you create what's called an isotope. Okay? So an isotope of a specific element has the same number of protons, because remember the protons can't change, but a different number of neutrons. So remember this picture from before where we've got the atom right here. So remember that the nucleus can't change, or the protons here can't change, but these neutrons, the blue spheres here, that number can vary, and that again, that doesn't change the element. And when that happens, that is when you create what's called an isotope. So example 1 here, it's very simply, which of the following represents a pair of isotopes? You're looking for an answer where the number of protons stays the same and the neutrons change. And the electrons, who cares about them? But the protons have to stay the same because remember, an isotope, it has to be the same element, just with a different number of neutrons. So you can see on answer C that you have 16 protons, so it's the same element, but you do have a different number of neutrons. Answer A, you do have the same number of protons, but then you still have the same number of neutrons. Those two are not isotopes. Okay, letter B, you've got 7 and 8. Okay, this is nitrogen, this is oxygen. Those are not isotopes. And then on D, you've got the same problem. You've got 26 protons and 29 protons. Again, it has to be the same element, so the protons have to stay the same, and the number of neutrons has to be different. So another example here says, all right, well, what's the difference then? Remember that this number up in the corner here, this is the atomic mass. What's the difference between carbon 12, notice the way they said that, carbon 12, carbon 13, and carbon 14? Okay, notice in this case, again, I don't write the atomic number because we already know what element it is. Sometimes that atomic number is not necessary. So how are those different from each other? Well, again, the protons can't change. So clearly all of these, as you can see here by the symbol, all of those are the element carbon. Okay, but what's different between them is clearly all three of them have a different mass. You've got a mass of 12, a mass of 13, and a mass of 14. So what's different between them is certainly the number of neutrons. Okay, carbon 12, because again, all three of these have just the 6 protons. Okay, but carbon 12, therefore, this one has to have 6 neutrons. Carbon 13, though, has to have 7 neutrons, and carbon 14 has 8. Okay, now, sometimes the question comes up, where do these different isotopes come from? They're just there. They just naturally exist in nature. Okay, as you can see here, I tell you that carbon 12 is the most common naturally occurring isotope of carbon. So most of the carbon that just naturally exists in our world is carbon 12. Okay, carbon 13 and carbon 14, yeah, there's a little bit of them, and some of them are really important, such as carbon 14. They use that for radiocarbon dating, so like for figuring out how long ago something lived, is they can use the carbon that's in our bones and to use that to determine how long ago something lived based on what's called the half-life of that radioactive carbon that's in our bones. Okay? Now, all of this leads to this idea of what are called average atomic masses. Remember that the number on the bottom of the periodic table for an element, as I said, it's the atomic mass of the element. Okay, but what I didn't tell you is, why is it not a whole number? Why did I say round that to the nearest whole number, and then you don't have to worry about the dot, the 0.01, whatever comes after the decimal point? Okay, but even on carbon, if you remember on earlier, on carbon it said C, carbon 6, and then I think it said 12.011, something like that. What's up with that 0.011? Okay, that's where isotopes come in. Okay, because what that number is, that number right there, that number is an average. See how it's the average atomic mass? It's the average of all of the different isotopes of carbon that exist in the world. Okay, of naturally occurring of the naturally occurring isotopes. Okay, a good example of this is chlorine. Okay, chlorine is a gas, and some of the chlorine atoms that just naturally exist in our world, about 75% of them, have 18 neutrons in them. Well, 17 protons, 18 neutrons gives you a mass of 35. Okay, but about 25% of, again, just naturally occurring atoms of chlorine actually have 20 neutrons. So there's 2 isotopes of chlorine that naturally exist. So if one of those isotopes has 20 neutrons, again, plus the 17 protons, gives you a mass of 37. Okay, so you can see that there are 2 naturally occurring isotopes of chlorine, and this number on the periodic table, which we find, which is about 35.45, is an average of those 2. Okay, well, what do you mean the average? Well, you use this equation right here. Okay, you take the percent abundance, so in this case it'd be the 25%, and you times it by its mass. So that would be a mass of 37. Okay, so I would take 25%, so I take 25, and write this down, might be good practice, times 37. And then the other isotope is a percent abundance of 75% times its percentage, or times its mass, which is 35. And I divide by 100, and you get an answer of around 35.5. Okay, and so all of these numbers on the periodic table come from an averaging of all of the isotopes. So it depends on the mass of the isotope. There's our 2 masses. But it also depends on the percent abundance, on how much of that naturally occurring chlorine or carbon is chlorine 37 or chlorine 35 or carbon 12, carbon 13, etc. Okay, and there is a device, it's called a mass spectrometer, that is actually used, and you put a sample of an element into it, and it tells you this is the percent of this element that is 35, this is the percent that we found that's 37, and that's it. Okay, example 3. The percentage of naturally occurring magnesium is 69.5% magnesium 24, 30.5% magnesium 25. What's the average atomic mass? Again, notice my work here. I took the mass times its percent, so I took the mass 24, times it by its percent, took the second mass 25, times it by its percent 30.5, added them up, divided by 100, and you get 24.305. Okay, now for the last one, I'm going to let you do that one. So as you can see, let me just give you a couple of ideas here. Let's do part A together. Which of the 3 isotopes is most commonly found in nature? Okay, well, you look right here at your percentages. Which is the biggest number? That's the one that's most commonly found in nature. So 92.23. Okay, so therefore, what's the correct answer? Certainly, silicon 28. Okay, now notice that in this example, they say silicon 28, but then they give you the actual mass of 27.98. Like in the previous example, number 3, I didn't give you the real masses. It's really close to 24, just like 27.98 is close to 28. But which number do you use? Do you use the 28 or do you use the 27.98? The best answer you can get is to always use the real mass. So if they give you the real mass in the problem, then use it. Okay, so use the 27.98. Now, and again, I'll give you a hint here. I'm not going to do this one for you. I want you to do it. But you know how you can check your answer? Look at the periodic table. Look at silicon on the periodic table and look at its atomic mass. Because remember, the atomic mass of silicon is the average atomic mass of these 3 naturally occurring isotopes of silicon that exists. So the answer to your question for letter B is already on the periodic table for you. Let's just see if you can find it.